We are going to be starting with sequence and series today. A sequence is basically a pattern of numbers that follows a certain rule. So let's just look at a couple of examples. I'll take the example of a very common series, which is the Fibonacci series, and I'm sure you would have heard of this. The series goes like 1 first term, 1 for the second term. Now the subsequent terms are the sum of the two consecutive terms. So the third term is basically sum of the first and second term, that is 1 plus 1, 1 plus 1 equal to 2. The third term is 1 plus 2, so it's sum of this term and this term over here. The next term is sum of 2 and 3, so just take the previous two terms and their sum. So 2 plus 3, 5. Next you have 3 plus 5, 8, and so on. So you can guess the term after 13. So after 8 you have 13. The next term is going to be 8 plus 13, which is 21. The Fibonacci series is extremely interesting because it is again and again seen in nature, in the branching of trees or the arrangement of petals. Also, if I take the ratio of two consecutive terms in this series, like say 21 by 13, and I can go to the next term also, which will be 34 by 21. So it turns out that this ratio, as we keep going on and on in the series, becomes a constant number which is very close to 1.618. So the ratio of two terms converges to 1.618, which is basically called the golden ratio. And this golden ratio, again, as I said, is in many places in nature. Coming to the next kind of sequence, another very interesting sequence, it's called the look and say sequence. So how this goes exactly is, the first term is 1, the second term is 1, 1, third term 2, 1, fourth 1, 2, 1, 1, and then over here you can see 1, 1, 1, 2, 2, 1. Now, why am I saying out these terms in such a manner, in such a strange manner? Like over here, I could have just said something like 111, 221, but I'm specifically saying there's 1, 1, 1, 2, 2, 1. So you can guess maybe the next term by looking and saying the digits of one term. So if I look and say the digits of this, now the digits of this are basically 3 ones followed by 2 twos followed by 1, 1. So this is the next term. So you can just go on and on. So both the sequences that I have taken over here are extremely interesting sequences, and I'm sure this would have given you an idea of what a sequence is, which is just a pattern of numbers following a set of rules. Now this concept, sequence and series, has many different applications in our practical life, in our real life basically. So for one of the very common things you would have heard is simple interest and compound interest. Simple interest, the amount of interest which is to be paid over a period of time for any kind of, say, investment, given that it is simple interest, that amount changes in a very certain pattern. That pattern is actually the pattern of something called an arithmetic progression, which we'll be learning further into this lesson. And that is one common application. Similarly, there is compound interest, and the term, basically the amount which is either payable or receivable by a certain party through compound interest, changes in a pattern that is a geometric pattern, geometric progression, which is also something we'll be looking into further into this lesson. So just mentioning a couple of examples of sequence and series that we see. Also, another thing is a lot of problems that we come across in real life can be reduced to just sequence and series problems. Even something as simple as velocity, distance and time problem can be reduced to a sequence and series problem. Just to give you an example, if I want to know how much time, say, a plane is going to travel, or how much distance rather a plane is going to cover in 10 hours. If its speed is given something around, say, 700 kilometers per hour. So I know that in hour number 1, it's going to cover 700 kilometers. Hour number 2 is going to cover 700 more. So it becomes a total of 1400. Hour number 3, 2100, and so on. So I know that in 10 hours is going to cover 7,000 kilometers. So something as simple as this can just be converted to a sequence and series problem where you have a first term is first hour, second term is second, third, fourth. So I mean, we have to look for areas where we can apply this concept. Now coming to the two main kind of sequences that we'll be looking at is basically, first one is basically the arithmetic progression. Now what is the arithmetic progression? Let's take the example of the first sequence I've written over here. So that is starting with 1, the next term is 3, then 5, 7, 9. Now you can easily guess the next term. You know that these are all odd numbers and the next term is going to be 11, then 13. Now what is it about this sequence? What is basically the defining pattern of this sequence? You know that each number, if I increase it by 2, I get the next number. So if I take 1 and add 2 to it, I'm getting 3. If I take 3 and add 2 to it, I get 5. Similarly, 5 plus 2 and so on and on. So basically, if I take the difference of any two numbers, so if I take the difference of 13 minus 2, 11 also, I know I'm getting the same answer 2. So an arithmetic progression is basically a sequence which has a common difference between terms. So if you take any two consecutive terms, you will get a constant difference. That is what defines an arithmetic progression. Let's take the next example. So I have minus 25 over here, then minus 20, minus 15, minus 10, minus 5 and so on. You know that the next term is going to be 0, followed by a plus 5, a plus 10 and so on. What is the common difference or that constant difference between the consecutive terms over here? That is correct, it is plus 5. So each term I'm basically adding 5. So minus 25 plus 5, minus 25 plus 5 gives me minus 20, minus 20 plus 5 gives me minus 15 and so on. So as you can see, each term has a common difference. Alright, so this is what is unique about an arithmetic progression. Let's just generalize this for any kind of arithmetic progression. So we know that one thing exists for every arithmetic progression, that is the common difference. Let's give this a variable d. Now another thing we require to create any unique arithmetic progression is the first term. Let's assign the first term the variable a. So first term, I'm going to assign this a. The second term, if I just take this a and add the common difference, I get my second term. Similarly, the third term, this will be a plus d plus d. That is going to be a plus 2d. Next term clearly is going to be a plus 3d, then a plus 4d, and so on. So an arithmetic progression is just formed by taking any first term, a random value for the first term. In this case, I'm just generalized it to a, and then keep adding the common difference d to subsequent terms. So a first term, then a plus d second term. This is the first term, second term, third term, a plus 3d fourth term, fifth term. So you know that if I just directly jump to say something like the 20th term, if I jump to the 20th term, you can see the relation between which term it is and what is the multiple of d. So for multiple of d to be 3, the term was the fourth term. Multiple of d to be 4 over here, the term was the fifth term. So multiple of, if the term is the 20th term, it's going to be the 19th multiple of d. That is the relation between the term number and the multiple of d. Okay, from this you can guess what is the general term going to be. General term mean, if I say the nth term, what is the nth term going to be? The nth term is basically going to be a plus n minus 1d. Alright, this is a very important result. You will have to remember this. So let's take the example of one of the sequences we saw, 1, 3, 5, 7, 9, and so on, and determine what is A, which is the first term, and D over here. Clearly the first term A is just 1. I can spot it directly and I can see that it's 1. Now to get the difference or common difference of the sequence, I need to take the difference of any two consecutive terms. So let's take something like 7 minus 5, 2. So I got the common difference D as 2. What will be the nth term or the general term of this sequence now? It will be A, which is 1, plus n minus 1 times D, which is 2, from the formula that we just learned. Alright, so this happens to be, I can actually expand this. I can expand this and simplify. And write this as 1 plus, this opens up to 2n minus 2. This gives me 2n minus 1. So this is my general term. Of course, I started with this from the formula a plus n minus 1d. This is nothing but a plus n minus 1d. And from simplification, I reduced it to this down here. How simple this is going to make things for me if I want to calculate something like the 100th term of the sequence. Now the 100th term, you'll have to, if say I figured out the pattern and I keep going one by one, 11, then 13, and so on, it'll take me quite some time. But now instead, if I use this formula, so it just becomes 200 term minus 1, which is 200 minus 1, that is 199. 199 is the 100th term of this sequence. Okay, so this question is find the 10th term of the arithmetic progression 1, 3.5, 6, 8.5. Okay, so I'll just write the sequence down again. Okay, so we know that the first term A over here is clearly 1. Let's find out the common difference D. I'm going to take the difference of the second and first term, that is just 3.5 minus 1, which is 2.5. I can verify that this is an arithmetic progression because if I add the common difference to the second term is 3.5 plus common difference 2.5, that gives me 6, which is the next term. And then again to 6, if I add 2.5, I get 8.5. So it is the sequence, and I need to find the 10th term of the sequence. So let me just write down the general term first, that is A plus n minus 1 D, that is going to be 1 because first term is 1, plus n minus 1 times 2.5. Let's just simplify this. This gives me 1 plus 2.5n minus 2.5, which becomes 2.5n minus 1.5. So now I have the nth term. This is going to be the nth term. In order to get the 10th term, I just have to substitute n as 10. So n needs to be 10. This gives me 2.5 into 10 minus 1.5. That is 25 minus 1.5, which is 23.5. So this is the answer, the 10th term. Very easy. Let's just look at another problem quickly. So this one is let a and be an arithmetic progression. So a n is basically the general term of an arithmetic progression or the nth term, for which d, so d is the common difference, is given as 12 and a3 is 43. So I have the sequences a plus 12, a plus 2 times 12. So this term is basically 43. And the question asks to find a1. So if I know that a plus 2 times 12, which is 24, is 43, that means a is just 43 minus 24. That is 19, and this is a1. So this is a1, 19. Actually simple. If the question could have also asked us something like find a17. What we do after that is we just put a1, which is 19, plus 16 into the common difference. So n minus 1 would be 16, as n is 17 over here. That is 12. So that would be 19 plus 16 times 12, that is 192. This gives us 211. That would be the answer.